wouldn't have it any other way.
Yeah, exactly. I am impressed with the turnout today, I have to say. This is a great group. Okay, let's come back over here. All right, we're going to do some more proving. Proof. All right, you ready for this? I asked this one on an old test one time. What number am I on?
7.
Okay. I get to problem 7, it'll probably be halfway through the exam. So, just kidding.
Everybody.
Let's see if it'll wait.
Maybe the final we will be.
Okay,
Probably not.
let's see. So here we go. Let A, B, and C. You guys are going to be a lot of you are going to be teachers someday. You'll get to tease your kids too. So
Number 7
mod. I don't know. Okay, so take 3 positive integers, A, B, and C. I would like to show that the GCD of A and B with C. You haven't seen this before, have you? Okay, good. Equals the GCD of A with the GCD of B and C. So we have to say that very carefully and put the parentheses in the right spot. That looks very intimidating. I asked it on a test though. It's really, once you know the approach, quite tractable. So calmly look at it and kind of think like in terms of the big picture of the different kinds of things we've proved. All right, I have the GCD of these 2 numbers. I'm showing that it equals the GCD of these 2 numbers. Anybody have a strategy for me?
So you let the D be the GCD of that first part and D prime be GCD of that second one.
So D and D prime?
Yeah.
Okay.
And show that they're equal to each other.
And show that they're equal to each other. That's definitely right. So that's kind of setting up some notation for us. And how are we going to show that they're equal to each other? Larry?
Show that they both have the same common divisors.
Exactly. Anytime you're showing, very good. Every time you're showing the 2 GCDs are the same, the trick is to show that they have the same common divisors, and then you know that they have the same greatest common. If they have the same common divisors, then the greatest one is the same on both sides. So let's see if we can make that work. So I'm going to say something like, let's see. I need a letter here. Let's let D, okay, be a, okay, this is, except Stephanie wanted to use D. I'm not going to use your variables, is that okay?
Yeah, that's fine.
Okay, great. I'm going to let D be a common divisor of the GCD of A and B and C. So in other words, I'm picking a common divisor on the left side. And I want to show then that thing divides both of the things on the right side. So I'm going to show that this D divides both of those 2 things. I'm assuming that D divides both of those 2 things right now. Okay. So if D divides the GCD of A and B, what else does that mean that D divides? A and B, right? Look, if D divides something else that divides A and B, then D itself divides A and D itself divides B, right? If you need to, draw yourself a little picture. You know, you've got A and B, we kind of drew this earlier. Here's the GCD of A and B. And now we're taking this other number D that divides the GCD of A and B. So it's going to divide both A and B, right? Okay. So D divides A and D divides B. Well, and we also already know that D divides C. Okay. Let's take a look at what we're trying to get. We're trying to show that D divides both of these 2 things. We're trying to get that D divides A. Oh, we already have that. Okay. So D already divides A, and we're trying to get that D divides the GCD of A and B, B and C. I'm trying to get that D divides the greatest common divisor of B and C. But we do already know that D divides both B and C. So does that ring any bells? If it divides B and C, guess what? It also divides the GCD of B and C. That's by problem number 2 from about an hour ago. It's in the review that we just did a little bit ago. Okay, so thus D divides the GCD of B and C. So D is a common divisor of A and GCD of B and C. So we started with a common divisor on the left side, we showed it was a common divisor on the right side. Now to go in reverse, I am perfectly happy, and this, yeah, Jeff?
Since in this review session, we have already proved that, we're not going to do it here, but would you want us to do that on the exam?
No, you can just state it as a fact from the review or from class. So, okay, you guys can cite things from class, you know, in class we proved this or that, or on the group work we proved this or that, or in the homework, right? You can cite those things. Just make sure that, you know, they really were done, you know. Because I was in class every single day. I'm pretty sure I remember what was covered. I love it when the people just, sometimes they just put down, by class, you know, that blah, blah, blah. I'm like, really? Which day was that? Okay, so anyway, so that's how it works. So then similarly, I'm just going to say similarly in reverse. I would actually accept that on a timed test. Just say that. What I mean by that is any common divisor over here is a common divisor over here.
Why do you have to show that?
Well, you have to show that they have the same set of common. So if I look, there's a set of all the common divisors of these two numbers. And then there's a different set of all of the common divisors of these two numbers. So you have to show that those two sets are equal. Set equality requires a proof of inclusion both directions. So I have only really written down the inclusion one way. I've said if you had a common divisor that's in this set of common divisors, then it's over here. But this is just saying, basically, you know, you have this and this that has to be proved. I wrote down this one and I'm just saying this is similar. I may as well, to save some time, right? And I would be totally comfortable with that. As long as it really is similar, there has to be a symmetry to the setup of the problem. Here there's a very, very nice symmetry between the A, B, and C. Actually, we could have written down a third statement, which would be that this whole thing is equal to the GCD of B with the GCD of A and C. So as long as you pick one of the variables and tie it with the GCD of the other two variables, you're going to get the same GCD. Am I making any sense? Hopefully. Okay, so similarly in reverse. So I'm just going to say it this way: the set the set GCD of A and B with C, and the set A with GCD of B and C have same common divisors. Thus, they have the same greatest common divisor. Right? If you have all the same sets of divisors, then you have the same GCDs as well. Being a little brief there, but I would accept that actually. I would accept. I would know that you know what's going on, and that's really what would be the most important thing to me. Okay. So far, so good. All right. Try a few more here. Won't keep you too much longer. I've gone through most of the things on my sheet here. Let's see, number 8. Just giving you some ideas of the different kinds of problems that I want you to be able to. Yeah, question?
You could not throw on that word because they can't see it.
Oh, I checked it. It's okay. I checked it a second ago. I think we're good. There's almost nobody who's not here, actually. It's like amazing. Oh, the other thing is, I think on the sample test, there was a true-false section. I will probably not do that. I will probably, because I hate, that was back in my youthful days before I understood how to teach very well at all. So I figured out eventually that a better thing to do is to tell you that it's true or false, and then give me a proof or a counterexample. So I will probably do that, so you're not sitting there guessing about it, because that's always frustrating. You're kind of in a timed pressure situation. Is this true or not? You don't know whether you should be doing a proof or a counterexample. So I'll try to do that. But on the sample test, you can take it as a true-false, just the way it's printed. But anyway, so here we go. Let's show that 120 times 91 factorial is congruent to 1 mod 97. Okay, see if we can crank this one out. Okay, yeah, I don't have. Okay, so when you see that problem, what comes into your mind?
Wilson's theorem.
Okay, very good. So we should at least state the thing. Wilson's theorem. What's it say real quick?
P minus 1 factorial is congruent to -1 mod n.
Mod P. Good. Okay, so there's Wilson's theorem. That's always good. You know that's probably what's needed, and so you just write that down. Okay, 91 is prime, by the way. 97. I said 91. You know why I said that? It's because 91 is like the smallest number that people think is prime, but it's not. We look at it, it's like, oh, it actually factors as 13 times 7, I think. So, but 97 is prime. Okay, so 97 is prime, we're good to go with that. So according to Wilson's theorem, 96 factorial is congruent to 1 mod 97. Negative 1, thank you. Just checking. Okay, so we look at the question we're being asked, we don't have a 96 factorial over there, so what do you propose we do?
Multiply both sides.
Say again, Chris?
Multiply to both sides.
Of what?
96, 95, 94, 93, 92.
Okay, so take the Wilson's theorem equation and kind of, which has 96 factorial in it, and write it partially as, do you have the answer, Lisa? Because I'm not ready for it yet.
No, I was gonna say we can also rewrite 92 as like 95, right?
Okay, yeah. We're gonna get to that. Let me slow down for a second. So the 96 factorial, see, here's the point. 96 factorial is close to 91 factorial. So I'm gonna write it as 96 times, Chris, this is what you were suggesting? And how far do you want me to go down to?
And then just stop at 91 factorial.
Good, yeah, exactly. That's the idea. Relate the two different factorials that you see in your problem, right? And all of this, of course, should be with a mod 97 on the end of it going all the way down. So I have the 91 factorial there, multiplied by all this other stuff. So what are you going to do? We haven't really talked about this today, but this should be automatic. You have a modulus here. You have these numbers, which obviously I'm not expecting you to multiply them all out. So what should you do with these numbers? Yeah, remember these numbers are congruent to any other number that's the same mod 97. So why work with such huge numbers? Just subtract 97 from everything, and we're going to get -1 here, -2 here, -3 here, -4 here, -5 here, and then we'll leave 91 factorial because we're happy with that. That's part of the expression we're trying to prove. And this comes out to be -120, right? So there's 5 minus signs, so it's a negative 120 times 91 factorial. And all that's the same as -1, so what am I going to do? Multiply 5? I'll get a 1, exactly. So I basically cancel the minus signs, okay? So, 120 times 91 factorial is congruent to 1 mod 97. This is a pretty simple question. What am I testing on this problem? I'm testing if you know Wilson's theorem. I'm testing if you recognize the 97 and 91 are very close, so you can do this little trick right here. And then I'm testing whether you're fluid with converting numbers mod 97 to better numbers for calculations. And this is why, if you have a calculator, I would lose so much in terms of what I was testing, because anybody could multiply this out, right? This coefficient out, and then reduce it mod 97 or something, and there wouldn't be much to it. Of course, this 120, I guess I could have made this a slightly harder problem, right? Because I could have done this. I could have changed this to, so this was 120, so I could have changed it to 23. Then it doesn't look quite as obvious, but of course, 120, we would have come to this point here. The reason I'm making the point is that 120 is bigger than the mod, so there could be a reduction done. So then it maybe wouldn't have been quite as obvious that, you're supposed to take 1 times 2 times 3 times 4 times 5. So anyway, so just being able to reduce numbers, there's a little bit of number sense going on in this class. Just kind of knowing how to deal with big numbers and so on is kind of important. Okay, I have, what else do I have? I started a little bit late. I think I have 2 more problems at the most. One of which is very similar to at least 2 examples you've already seen, so I don't think it'll be too hard. Let me do the one that's maybe slightly trickier first, and then I'll show you the easier one second. And then we'll be good to go as far as I'm concerned. I'll have done everything that's here. So, so let's try this one. So this, what number am I at? Number 9. Number 9. Prove if 2 does not divide A and 3 does not divide A, then A squared must be congruent to 1 mod 24. Okay? Get this thing charged up again. Any thoughts? Say again? Chinese remainder theorem. Hey, that's a great idea. If you look at the mod, right? If the mod says 24, if I could prove that it was true mod 8, and if I could prove that it's true mod 3, then I would know that it's true mod 24. Of course, you're thinking of 24 in terms of prime factorization like that, and so you're breaking the mods this way. It doesn't do you as much good to break it differently. So if you said, well, I'm going to break 24 down into 6 and 4, well, now your mods aren't relatively prime, so you're going to have to go do something like this over here, which is a bit more of a complex approach. So it's better you have the choice here, right? You can choose how you want to factor 24. So 8 and 3 is good. So it suffices to show that A squared is congruent to 1 mod 3, and A squared is congruent to 1 mod 8. Let me just remind you guys again, and this is just in terms of getting partial credit. If Roger says he's going to solve this problem by the Chinese remainder theorem, and then the whole rest of the solution is just total nonsense, if he wrote down that he's going to use the Chinese remainder theorem, that is worth something, right? You should be writing that down. Even on the homework that I've already bothered you guys about this once, but on the homework, some people weren't really giving due credit to the CRT in your homework. So try and do that on the test. Just put that down. You're going to use the CRT, and then I can give you some points for that. So suffices to show by the CRT, let's just put it down now before we forget. So by the CRT, we're gonna do that. Okay, so based on that, where can we go with that? We've now created two problems out of one. We need to show this and this. Maybe we should start with this one first, because smaller mods are easier. So how am I going to show that a squared is congruent to 1 mod 3? Brittany? Oh, you want?
Well,
I don't care. Somebody.
Fermat's little theorem, use Fermat's little theorem because 3 does not divide A.
Oh, okay, so 3 does not divide A, so there's a Fermat's little theorem application. So by Fermat's little theorem, since 3 does not divide A to the P minus 1, which is A squared, is congruent to 1 mod 3. That's good. Okay, I guess maybe I should at least, in the review session, write it down once. Fermat's little theorem, right? P does not divide A, then A to the minus 1 is 1 mod P. Okay, good. Okay, so that's absolutely right. Everybody okay with that? Okay. By the way, if you didn't have to use Fermat's little theorem, you could say, well, if A is not divisible by 3, then in the world of mod 3, it's either congruent to 1 or negative 1. Now square both sides, or square either one of those, you get positive 1. So you can just brute force it, but why do that when you've got such a nice way to do it here with the theorem? Okay, what about the mod 8 piece of this? Yes, Lisa.
Well, since 2 does not divide A, then A must be congruent to 1 mod 2.
Okay, so 2 does not divide A implies A is congruent to 1 mod 2. I am with you. Means that A is congruent to 1 mod 2. Bora?
You could just do the same thing you did for the 3. Say since 2 doesn't divide A would have to be 1, 3, 5, or 7 in mod A, and just brute force it by squaring them all.
Okay, so in mod 8, yeah, so if this is true mod 2, is it true mod 8?
And more.
Okay, can you make this mod bigger? Leave everything else the same. Can I make the mod bigger? No. What I can do is I can make the mod smaller. I could, okay, so if this was, let's say this was mod 20, right? If it was mod 20, I would be free to change it to mod 10 or mod 5 or mod anything that divides 20. You can always make the mod smaller, but you can't make it bigger. So you can't go up to mod 8 from here directly, right? So instead, Bora's approach is exactly the right way to do it. Basically, A is an odd number. So modulo 8, it has to be congruent to 1, 3, 5, or 7. Okay, so A is congruent to 1 mod 8 or 3 mod 8. 5 is the same as negative 3, so heck, let's just use it. And 7 is the same as negative 1 mod 8. Those are your 4 possibilities, and if you square any of them, you're going to get positive 1 mod 8. So A squared is congruent to 1 mod 8. So what that means is that, let's write our conclusion. I would like conclusions to be written out here on something like this. So the conclusion then would be A squared satisfies, I like it when people set up the system. So we have the system x congruent to 1 mod 3 and x congruent to 1 mod 8, right? So both of those are true. And so how do we sort of proceed with the, I want to make sure we know how to do the punchline here.
By the uniqueness
By
part
the
of the
portion of
Chinese
the
American
uniqueness of the Chinese American
I must have
theorem.
written that on your paper. I was a little fussy about that point, I'm sorry. I had a bad day on Tuesday, read like for 8 straight hours. Yeah, before I go to the uniqueness part, what else would I maybe want to note first here? 1 is also a solution. I can clearly see if I put 1 for x, it's just obviously a solution. So obviously, let's just write that as well. 1 is also a solution. So by the uniqueness part of the CRT, a squared is congruent to 1 modulo the product of the mods, which is 24. Exactly. Make sense? Okay, great. Have I ever asked you guys anything with about the decimal, the digits in the decimal representation of a number? So like how many zeros does a certain number end in?
We had some homework on
It
it.
was on a practice quiz, but not on anything else.
We had homework on it.
Did we have one on the homework maybe? Okay, let me just, all right, I'm gonna throw one more at you here, and then this will be the last one, okay? Well, actually, let me mention a couple of things real quick. So I'm gonna write down a problem, and then you guys can tell me if you want me to do it or not. Because I think you may already know how to do this problem without me going through it all. If I can find it. Yeah, so if I ask you this question, so what number am I on, 10? Okay, let me write this down, and you guys can tell me if you want me to go through it. Okay, 'cause I don't want to skip something that we need to review. So find the remainder when 7 to the 2006 is divided by 3,800. Would that be worth doing? Or do you know how to do it? Let's see, it would help if we had a factorization of 3,800, just so you know. I just want to make sure. So this is, it's 2 times 19 times 100, first of all. And then you can go from there. 100 has 2 factors of 2, so it's 2 cubed, and then 2 factors of 5, and then 19. So there's the factorization, right? So we want to figure out what the remainder is when 7 to the 2006 is divided by that number. Nicole?
On the test, are you going to tell us what the factorization
I
is,
might.
or just, okay.
I was thinking of giving you like a 5-digit number that's not obviously prime or not, and let you spend 45 minutes trying to factor it. No, I'm not interested in like making you spend a huge amount of time on that. Yeah, exactly. Without the benefit of a calculator, it could be kind of a pain. Okay, so but 3,800 isn't too bad. This one I would expect you to be able to do, because you just, the 2 zeros at the end, so it's like 38, and then you just tack on 2 more zeros. But yeah, if I gave you like a number like 123,456, probably I would give you a factorization, because I'm not interested in making you spend too much time on it. So anyway, how do you do this problem? I guess that's the question.
Well, you change your mean theorem.
Okay, you use the CRT, so we'll just sketch a solution here maybe. Use the CRT, and so to do that, basically we need to do what? What are the mods of the equations you're going to work with? 8, 25, and 19, right? Okay, you can't break down the 8 into a 2 because it's not relatively prime to itself. So, for example, we need to figure out what this thing is congruent to: mod 8, mod 25, and mod 19. Okay, so let's see if we can do that. So consider 7 to the 2006, mod 8. Oh, mod 8. What do you suppose we can do with that? Okay, everybody should be thinking by now, change these to negative. You know, if you see a number close to the mod, switch it to negative. So this is just -1 to the 2006 mod 8. So that's just 1 mod 8. So I'm going to start writing my summary maybe over here. This is what you would write at the end of the solution, but